In the last video, we looked at chain reactions. And now that we understand those, we can start talking more specifically about the practical applications of them and of nuclear fission in general. And in this video, I want to focus on nuclear explosions, such as the atomic bomb, and understand how they work. Specifically, this video is aimed at understanding the necessary conditions under which a nuclear explosion will occur. First, I want a quick recap of chain reactions. In the last video, we spoke about how one uranium nucleus, when it undergoes fission, will produce a few things. So the first thing it will produce is the daughter nuclides, the smaller fragments that it's breaking up into. But in addition to that, and importantly for our purposes, it will also release some neutrons, generally 2 or 3. In the example we saw in the last video, it was 3. And the reason why that's important is because it was the absorption of a neutron in the first place which caused this uranium nucleus to undergo fission. That means that when more of these neutrons are released, if one of these neutrons that is emitted can be absorbed by a further uranium nucleus, then that neutron might cause this second nucleus to undergo nuclear fission as well, leading to a chain reaction which can continue to occur without our active input. The problem with this picture is that we cannot be sure that this step will actually occur. If we think about it, a nucleus is a very small target. And so there's actually a really small chance, if I just had one uranium nucleus sitting there, and I fired 3 neutrons in its direction, there's actually a very small chance that one of those neutrons is going to be absorbed by the uranium nucleus, because the nucleus is such a small target that it's actually more likely that the neutrons will just miss it entirely. So how can we be sure that a chain reaction will actually occur? To help us understand when a chain reaction will actually occur, I want us to look briefly at the volume to surface area ratio of a sphere. If I have a very small sphere, then its volume to surface area ratio is low. In other words, most of the stuff, let's say I've got a ball of uranium-235 nuclei. So each one of those dots is a uranium-235 nucleus. If it's a very small ball, then most of the uranium nuclei in that ball are actually towards the outside of the sphere. The surface area, the proportion of uranium nuclei towards the surface is higher than the proportion of uranium nuclei that are packed in towards the middle. On the other hand, if I have a very large sphere packed equally as tightly with uranium nuclei, and I'm not going to cover the whole thing as tightly because that'll take me too long, so I'll do it a bit more spread out, but you can picture it yourself. If I draw a much larger sphere, then now the volume to surface area ratio is a lot higher. In other words, there is a much higher proportion of uranium nuclei towards the center of my sphere than there are towards the surface of it. Whereas in this ball, most of the uranium nuclei were out towards the surface. When I have a much larger sphere, most of them are actually what we might call towards the middle of the sphere, while there's a much smaller proportion of them that are around the outside. The reason why that's important is because imagine a uranium nucleus undergoes inside that ball, undergoes nuclear fission, and emits a neutron. Whether or not that neutron is absorbed by another uranium nucleus will, in part, depend on how many uranium nuclei it has to pass through until it's out in the open air. So if I have a very small ball of uranium nuclei, that means it has this is a small volume to surface area ratio, which means that there is not enough uranium nuclei towards the center to make sure that a neutron released will actually be absorbed. Because it's much more likely, if a neutron is released by one of these nuclei, it's actually a lot more likely that that neutron will simply fly off into space, not being absorbed by another nucleus, and therefore not causing a chain reaction. So, a small volume to surface area ratio means that it will not have enough mass, not enough stuff to sustain a chain reaction. On the other hand, if we have a very large, that's not very large, that one, let's draw it a bit larger. If we have a very large sphere full of uranium-235 nuclei, then that has a larger volume to surface area ratio. In other words, there's a much higher proportion of those nuclei packed towards the center of the sphere, and so it has enough mass for a chain reaction. If this picture is clear, then we can start using some specific terminology here. So the key term that I'm going to introduce in this video is, let me introduce it first. If we think about that larger sphere, the point at which the sphere becomes large enough to support a chain reaction, in other words, the point at which I have enough stuff that I'm sure that a neutron released will be absorbed by another nucleus, is called the critical mass. The critical mass is the key term from this video, and it's the mass of fissile material. If you're not familiar with that term fissile, it's from the word fission. Fissile material is material that readily undergoes nuclear fission. So the critical mass is the mass of fissile material required or needed to sustain an uncontrolled chain reaction. When I have a critical mass of uranium-235 nuclei, for example, I'm so sure that more than one of the neutrons released by one nucleus will be absorbed by further nuclei, that the number of nuclei undergoing nuclear fission will continue to grow exponentially until virtually all of the uranium nuclei that I have undergone fission. And since each nucleus undergoing fission releases energy, if I can create an uncontrolled chain reaction where they are all undergoing nuclear fission, that will release an enormous amount of energy, such as in a nuclear explosion in an atomic bomb. So let's think now about how an atomic bomb actually works. The way an atomic bomb works is we start with a bomb. So those pictures that you see of the atomic bomb sitting there, this kind of like big metal hunk inside there, it's actually split into two separate chambers, where each chamber has the fissile material, but each chamber on its own has a subcritical mass. In other words, in each one of these two chambers, there is not enough of the fissile material for a chain reaction to be sustained. The way that the explosion is set off is by removing the barrier between the two chambers. Once that barrier is removed, we now have both masses combined to form a critical mass of fissile material, which will set off this uncontrolled chain reaction where all the uranium-235 nuclei will undergo fission in a very short amount of time, releasing an enormous amount of energy and causing a nuclear explosion.